So I hope everybody can hear me. Fadi, if I start breaking up or anything, just let me know. I'm getting used to these telemed. It's kind of fun doing webinar from home because you get to have a beverage and give a talk, right?
Very nice.
So we'll get started, and I'm going to share my screen. And can you see that okay?
Yeah, absolutely.
Yes.
All right. So today's webinar, we're going to talk about the LolliPOP system. I'm Sean Standard. I am pediatric orthopedist from Baltimore, Maryland. I work at the Rubin Institute for Advanced Orthopedics at Sinai, the International Center for Limb Lengthening. This is my email address. If there's any further questions, that's our website. And the LolliPOP kind of came about. It's been an idea that I think I've been kicking around with Jim Orsak, one of the other co-inventors, for about a decade, about 10 years. And thank goodness Pega liked our idea, and Fadi kind of ran with it and turned it from an idea into something pretty wonderful. This was from our first case back in January 2018. And today we'll kind of go over, you know, the intended use. Some of this is going to be a little basic, treatment existing products. What are the features and benefits of the LolliPOP, implant specifications, biomechanics, and that's really important. Like, how does this compare to the other blade plate systems that are out there? Implant instrument trays, surgical technique, and kind of a sawbones guide, along with a similar real case that we can give you some pointers and how this thing works. We can answer some questions, and I have some case examples at the very end just to kind of show you the variety of things that you can do. Basically, any proximal femoral osteotomy you can do with the blade plate. So the intended use, you know, this is a proximal femoral osteotomy set, and if you look at it, I'm a limb deformity, limb lengthening, and I have my own selfish need for a nice 130-degree modular blade plate. But looking at the world of pediatric orthopedics and remembering back in the day of my general neuromuscular clinics, you know, we tried to make the perfect, you know, neuromuscular VDRO plate, taking all the elements from all the different plating systems I've used and kind of making them even better with a modular design, and I'll show you why that is so advantageous. But you can do varus osteotomies, valgus osteotomies. Now, leg calf Perthes disease is a special. It's about a third of my practice. I honestly don't do proximal femoral osteotomies for it. I do hip distraction, but if you are a varus osteotomizer for Perthes, it's there. You can do the salvage valgus as well. Skiffy, perfect, and I can't wait for our adolescent plates to be widely available because it's the perfect plate for an intratrochanteric osteotomy for a residual skiffy deformity. And in my world, the PFFD or CFD, I use this quite often. So if you look at the hip deformities, you're looking in the coronal plane, you have coxa vera or coxa valga. You're looking at the sagittal plane like this skiffy, and if this is pinned in place and heals, this is going to be, you know, an extension deformity, which will need eventually a flexion deformity to correct that. And then you look at the you know, prototypical anteversion, you know, end toeing and either external or internal torsion of the femur. And so we know our goal is between 120 and 135, but this can be, you know, variable. You know, that's what we want. We deal with coxa valgas. We deal with coxa veras. Now, sometimes we actually want to create a coxa vera, mild, or a coxa valga. You know, I have a young boy with a kind of a modified Dunn osteotomy who's walked on it, and he's now got a non-union and the head's falling back off. So I want to tilt this thing up into a high valgus angle to get it to heal. And that's what this blade plate will let you do. And so this is the rotation. They have a really neat little rotational guide that you can use if you're more comfortable with a very specific amount of rotation. And this is just showing how a previous fixed angle blade plates, you get the extension or flexion depending on where you make your initial footprint. And we took this into consideration to make this more accurate and easier to do. So what are the drawbacks of the existing products? And so I've used all of these products in the past. Larger incision for the fixed angle device because you have to have enough room to get it in. Inadequate cannulated designs, and that means that the very first cannulated design, Synthes, only the bevel was cannulated, not the entire plate. Smith and Nephew Orthopediatrics came out with entire cannulation of the blade itself, which improved it, but you're still using a chisel. And so you put your guide wire in, and with a fixed angle device, you have to calculate your angles, subtend angles off of different wires, and it's all doable. If you do a lot of proximal femoral osteotomies, you can use a fixed angle device, and that's great, but can you make it better? And that's the idea that we ran with. And so the multiple chisel passes, I hated. You could get your chisel impinged on the wire, and it would start advancing your wire. You could get stuck. You have to get the incarcerated chisel to get it out, and all the passes in and out, you're really losing fixation. The other is that you make your osteotomy with your chisel in place, and you pull your chisel out, and then you have to put your blade plate in. That can also induce an area of where it goes, even with a cannulated design. And once again, you're losing fixation every time you push in and out. Rotational instability, if you have a DHS, the fragment can roll around the screw of the head. That screw is in, but the head can turn on that screw, and you don't have any rotational stability. The keyed element tries to fix the screw inside the blade plate, but the bone itself can still rotate on the screw. And proper biomechanics is one of my huge pet peeves. And you'll see that some of these valgus plates have medial offset. If you're doing a valgus osteotomy, you have to have lateral offset. If you're doing a varus osteotomy, you have to have medial offset. And you see these designs that are completely counterintuitive and wrong. And so the inventory, from a cost and supply chain management is an issue. And we tried to come up with a design that would reduce the inventory, have very discrete, trays, and have everything you need in 2 trays. And the fixed angle devices is unforgiving. So that's why we get good at putting blade plates in, because if you're off, it is what it is. You can take it out and bend it, and we all got the plate benders out. And those things can be problematic. And the way we do that, and this is with the modular blade plate system. So if you look at it, this is a chisel free, which is great because you just put in the chisel blade once and you're done. You have better fixation. You can do varus osteotomies with medial offset, valgus osteotomies with lateral offset. This is kind of the exploded view of a typical varus plate, 90 degree, and they come in different degrees so you can change your angulation on the fly. So what are the features? Well, the varus valgus plates range from 90 to 140 degrees. It's chisel free. The osteotomy is actually performed with your chisel blade already in place. So you don't have to reintroduce a blade into a mobile fragment. The cannulation is all the way through the blade, which gives a great, great guidance. The modularity provides surgical flexibility. So if you're in the middle of the case and you don't like how much valgus you produced, or you produce too much varus, you can simply adjust that by switching out the modular plate. Now, having said that, your flexion extension is not modular, right? And that might be LolliPOP 2, I don't know. But at the point, you have to be careful of making that first footprint, and we'll talk about that. Intuitive instrumentation, we're trying to really kind of make all of this make sense and user-friendly. And the last one was the blade construct. It's extremely stable in both rotation, flexion, extension. No cutouts that we've experienced, no failures, and we'll talk about that in a second. So these are the implants, and I'm going to let Fadi jump in for a second and kind of take you through some of these specifications.
Certainly. So we have three different groups: infant, child, adolescent, following the typical plate sizes that currently exist, with the range of blades ranging from 25 to 70. The blade components, in case we need to refer them in the future, the buttress is what we call is the part of the blade that will engage into the plate, and it has a bevel design that countersinks into the plate, and that's part of our patented technology that makes the two components really integral one into the other. And then you have a keel that gives it additional bending stiffness, but also rotational stability. If you look on the left image at the front view of the blade, you see it's almost like a Batman sign geometry. So that prevents any lateral cutouts or any rotational issue. So we've got some guests. So
You'll get a bit. Yeah.
It's in a nutshell the blade features. And the blade is sharp. So unlike your chisel, no matter how good your standard one-piece blade plate set is, your chisels will become dull, and with time will require more trauma, more force to insert. This blade is sharp. Obviously, it's an implant, so it's single use. You always have a sharp implant to introduce into the bone. We can go to the next one, Sean. So here you have the range of plates. You see here the infant, child, adolescent, and HD, heavy duty. So it's kind of a young adult size plate. In order to stay with the standard sizing that we're familiar with, infants is essentially a 2/7 system, child's a 3/5, ado and HD are 4/5. The various offsets increase, and so is the plate width and thickness as you get to larger plates. The first hole in the plate allows you to do, it's both a polyaxial hole that allows you to either capture the most proximal segment or do compression across the slots. The remaining holes allow you the option of either introducing a locking screw or a standard cortical screw. And we designed the plate to be as low profile as possible while maintaining very high strength. We'll see that in the next slides. As well as Sean also mentioned already, but we offer both, not only is the varus place offset, but the valgus place offer also an offset to lateralize the shaft. So that's essentially the way the head moves over to the side. As I mentioned, screws are 2/7, 3/5, 4/5, quite an intuitive sizing. None of it should be mixed. So if you're working in infant or child or adolescent, they're not interchangeable. Everything infant and child is packaged in one tray and is driven on a 2/5 driver. Adolescent is driven by 3/5. And essentially the screw lengths are standard that cover the range of the bone diameter. Here we see the infant child tray. So we tried to make it as compact as possible of an implant tray. You have on one side all the infant plates ranging from 90 varus to 140 valgus. And on the other side, the child plates, same angles, and the blades on either end. And internally, you have the caddy. We have multiple screws of each length. So essentially, everything in one tray allows you to do a bilateral procedure. This was really geared for those bilateral VDROs, very common procedures. As Sean mentioned, the adolescent tray will be coming in the fall. And the adolescent tray will be a secondary tray that will house all the adolescent components. We can go to the next one, Sean. And here we see the 2-level instrument set.
Did it go for you?
Yep, it's perfect. So here's the 2-tier instrument set for infant child. Sean will be going through the technique step by step, so we'll see every one of these instruments. The only disposable part of the tray are the guide wires onto which the blade goes over. Everything else in the tray is reusable. And the adolescent tray that will come in the fall with the implants will not be a standalone tray, will be an add-on tray to this set in order to not double multiple components.
And when we kind of, the royal we, Fadi, really came up with some great ideas with some of the instrumentation, with some of the other problems that we routinely run into with other proximal femoral osteotomy sets. And every set has, you have your special instruments. I really like the metal triangles, and we have triangles, for different angles, even though you don't have to do that. If you're kind of old school, you still want to do that. Our triangles are here. We have different osteotomy guides. This is a neat little invention of Fadi's for that 1-1 wire, and we'll go through all this. But we really tried to make, these are standalone trays. Everything you possibly could use in a proximal femoral osteotomy is kind of contained in these trays. So I'll let Fadi talk about the biomechanics. Did that switch for you, Fadi? You're still muted.
Perfect. Yeah, I just removed my background because it makes the whole thing work extra hard to try to create that virtual background. Yeah, so a lot of the main concern that we hear from people is the strength of the construct, and it was heavily tested, and what we spend the most time on from day one was the blade plate junction. We want to make sure that that thing was extremely strong. So actually, the blade plate, the connection will not fail. It takes loads way greater than any other component can resist. So as you can see on the image on the right corner, our plate, like many plates, will fail through the most proximal screw hole at the narrowest portion. And that's actually, we're talking above recommended usage loads, but that's a preferable failure site. Because if ever, you were to put a very small plate on a child that you lose to follow-up and they become an obese adolescent and break, it'll break through a screw hole, which makes the whole thing much easier to remove. Here, in comparison, we have a Synthes blade plate that was tested on the same construct that broke at the transition of that T profile, which would be much more of a catastrophic failure. On the next slide, we'll see some head-to-head. So essentially, when comparing our LolliPOP to the finite element images that you see are the orthopediatrics blade plate in comparison to the Pega medical, and you see that expressed on the left here in bar graphs. So essentially, our strength is quite comparable to the Synthes Capos plate, which is very much so the standard blade plate, and about 10-20% stronger than orthopediatrics plate. So we're very, very pleased with that, with the strength of that connection. And as you can see from the image, there is so red highlights zones of high stress while blue are very low stress. And because of the countersink design, you can see that the whole interface between the two components is not a zone of high stress. If there are more specific questions on testing at the end, I'll be happy to answer them.
So we'll go on with the surgical technique, and this is kind of one of our, little play slides that we kind of considered the LolliPOP as kind of like these little building blocks, and you can really build anything that you want. And if we look, so this was a little lab that we did and kind of put together for a couple different meetings. And so this is, I always laugh, this is my biomechanical lab. This is actually my garage and needs organizing. But this is where I do a lot of my sawbones. And you can see this is a Coxa-Vera model akin to a congenital femoral deficiency, or PFFD, which is one of my, big parts of my practice with congenital limb deficiency. And so if you look at other fixed angle blade plates, you'd have to go from tip of the trach to center of the femoral head to kind of create an angle. So you're going to recreate the neck shaft angle of 130 degrees, or the whole, it's fine if you want to do that. And there's all kind of ways to do that. In the same way you subtend your angles off with a 90-degree blade plate to get your certain amount of varus. But the whole premise of this set is to do a 1-1 wire. You just put a wire in the center of the head, and you put that wire in the center of the head and you're done. And then your blade does the rest as far as which plate you choose onto that blade. And so if you look, this is the initial kind of wire insertion. And I'm trying to move myself, there we go. And so if you have that initial guide wire insertion, you're trying to get to that 1-1 wire. And if you look intraoperatively, this is the same patient that we just saw momentarily, this little guy. So you do an arthrogram and you actually can see the femoral head. And now you can guide your guide wire straight into the femoral head and AP lateral, a little anterior, that's okay. And now that's your final position. And you really look at it on a true lateral because you want to see this bullseye. So I'm right in the middle of the femoral head. So I know where my guide wire is, and that's where my chisel is going to go. And so if you put your first wire in and you like it, but you're not super happy, this is a great little instrument. This little instrument can kind of create different 5 degrees angulations from, so if you wanted 5 degrees off of this, you would then put your initial guide wire and say, I need to make it a little bit better. You put your second guide wire in, depending on the angle you think, through your little gizmo, and this is a 90-degree, or you can do a 130-degree angle. And you put it perfectly in. If you like doing it freehand, do it freehand. I'm a freehand kind of guy. But this is a great little little device. Once you have your guide wire in, you use your depth gauge and you look at the size of your plate. You measure it on this little depth gauge, and you can do physeal sparing or transphyseal. So if you look at this, you can stop, or you can go across the physis and engage the epiphysis, depending on what you're doing. And CFD, sometimes I like to go all the way across and grab that epiphysis because I have a big cartilaginous neck I'm trying to get to solidify or ossify. And this is an example of a little the child that we're looking at, and you can see where the blade plate kind of ends up just probably across the physis. But the nice thing about a blade plate opposed to a screw, look at this. This is a cyst that I fixed prophylactically after taking out a failed locking plate, bone grafted, and I drove this thing as far as I could because all of this was cyst. This is a little bit after the surgery. And I got into the epiphysis a little bit, so I'm in the physis. But if you look at 6 months later, it's grown off of that. And remember, it'll grow off the physis. It's not going to hurt the physis. And that's another thing that, whole nother discussion. But you can see now the cyst is completely healed. He's grown off the physis. The physis is still growing. So you can kind of decide which you'd like to do. So with the guide wire insertion, you have your 1-1 position. You have triangles in the set. If you like to look at your angle, make a certain angle, subtendon angle, and you have the guide wire positioning little device. So now you have the guide wire in, and you want to set your footprint of your chisel blade. And this is going to induce either neutral, flexion, or extension. And if you look, this is the Sawbones model. This is an old prototype. It's a little bulky, but this is the nicer version with you have your cortex breaker and you have, and I call it the flapper, this little guide that you can kind of push down on the bone. You can dial in how much flexion or extension that you would like to produce. And then you create your footprint by breaking the cortex. This helps the entry in of the blade plate into a hard cortical bone, plus it sets that footprint for your flexion or extension correction. So you then put your device together. You have your blade, chisel blade length. That then connects to the connector shaft, which then connects onto a slap hammer, or you can put it onto a handle. And you put it over your guide wire, and then you mallet either with a normal mallet or the slap hammer, and you push it in place. So this is another from the operative guide that you're connecting all of these little components together. And you then have your blade chisel on your driver, and you're driving it into position. And this is the intraoperative fluoroscopy view, driving it home. And you always want to, and I think it was previously stated, and I jumped over it, leave 10 millimeters, 5 to 10 of protrusion of the plate assembly. It's going to be very important when you connect your blade plate. So you can see that I'm driving the blade in, and I leave just a little bit. That's probably about 6-7 millimeters out. You want enough of this little Batman sign, right, or little stop sign we call it, to be able to engage onto the plate. So at this point, your blade plate is in. So at least the blade part, or the chisel blade. And now you can use the handle that you just put to guide your osteotomy. These are osteotomy guides. This is for varus deformity. This is for valgus deformity. If you look, the orange part of the osteotomy corresponds to the throat thickness of the medial offset. So this tells you this is the closest you want to be to the blade plate. If you go any closer, you're going to run into your offset, and you're going to have to chisel away. And I'll show you some examples of that when I did it early on. Again, with the valgus plate, you'll see the little stop sign, right? This is our little yield sign that's going to go into our blade. And I've made my cuts too close. And then this will then run into my distal fragment, and I have to do a little bit of carpentry. And so you want to make sure that you give enough space for your, and I'm sorry, this is a varus deformity valgus osteotomy. This is a valgus deformity varus osteotomy where we're doing a closing wedge, and you're going to have bone-to-bone contact. So one of the early frustrations was trying to get the plate onto the little chisel blade and have it locked in, because it's a very intimate fit. And then you put in your connecting screw to lock it in place. Libby Weber up in Rochester just came up with a great little technique. Your guide wire is in. This is a drill guide. You put the drill guide with the most multi-axial tip over the guide wire, and you push it, and it locks that plate right in place. And then you just put your screw in. And it's even become part of the technique guide. But that was one hurdle overcome with a brilliant idea. So here is my chisel blade in my coxavera, and I've now attached my valgus plate. This is 130-degree valgus. The valgus plate's 130, 140. We have 120. So we have 120, 130, 140. And if you look, this is a newer design. You'll see some of the x-rays, they have a very large knuckle. That knuckle has been removed for better bone contact and better positioning of the plate. And so this is my osteotomy. You can see that I did my osteotomy past my little connecting point of the chisel blade and the plate. And I did an opening wedge osteotomy. You can see, and even in surgery, you'll have these little bone fragments that you might have to my osteotomy, way too high. So you can see, and these are very tiny children, but that's the locking portion of this design. So my plate can be off the bone and act like an internal X-fix and lock this and still be extremely strong. And I'll show you the end result. So what happened with this? So I take that little piece and I just put it back in as bone graft. And I do that quite often in surgery. We lock it back in place and you hold it, and then you start your verification that if your neck shaft angle is what you want. So the first thing is, once you lock your plate on, you can then reduce it with a verbruge or your fingers. And if you look, this is another case of DDH, child getting a varus osteotomy. And you can see that I have the plate in place. I have it connected to my 110-degree blade, and this is the neck shaft angle that I have achieved. You then can check your neck shaft angle intraoperatively and see if you like it. The beauty of this plate is that if you want less, you then choose the 100-degree plate. If you want more, you choose the 120-degree plate. And that starts changing your neck shaft angle. And you can do this simply by unscrewing this little screw and putting a different plate on. And that's the beauty of the modularity. This is the derotational device, another invention of Fadi's, which is really, really neat. You lock this in place stable with two drill guides that go into the locking screw hole, and you have your rotational gauge here. You then put a wire in at the 0 position, you loosen your verbrugge, you rotate to your desired amount, and then you retighten your bone clamp, and then put your locking screws in, and you have a very accurate derotation. The compression screw, as we talked about, the first hole, it can either be a multi-axial hole or multi-directional, or a compression, giving you 1 to 2 millimeters of compression. These are the locking screws that we talked about. These are very intimate. So I am notorious when I use locking plates of different companies. I freehand everything and I cold weld. Do not do on this plate. You need to use the locking drill sleeves. It's a very intimate fit, but very strong. You do want to add a couple millimeters on to your measurements just because of the heads. This is where we are with our bone model. We have now got it to the point where we have our plate in place and we have our drill on. We reduce it under fluoro. It looks good. We go ahead and fill up the holes. And this is what we started with, this Coxavera, and with this very simple, modular blade plate system. And if I think this is too high of a neck shaft angle, I could have gone to a 120. If my 1-1 wire wasn't corrected, I could have switched to a 140 to get more of a neck shaft angle. This is the flexion, correction. So this is an extension correction. We had a flexion deformity, and we extended it by rotating the keel of our chisel blade. So this is the little guy who we started, actually a little girl, and this is the end result. This is her little epiphysis. So she had, probably a neck shaft angle starting about 60, and she ended up with 130. This is when I do ankle work as well. So I removed wires and then an arthrogram, and you can see the blade plate riding a little high, but very strong. All of this is cartilage. You can't see anything, and all this is going to fill in over time. You can see how strong the plate is. It's sitting off a little bit. You can chisel away the little knuckle. You don't have to. As long as it's sitting in well, it'll do fine. And if you look, this was the previous design. That knuckle is now gone. This comes straight down. And because of that. So the other instruments, I think one of my favorite instruments is the nipple verbrugge clamp. And it's awesome. It holds on. You can derotate, you can clamp. And so this is like one of my favorite instruments. The point-to-point reduction forceps, you can see if you need control of the proximal fragment, this is something else. You don't want to have to go find one. It's already in the set. Implant removal, I have inserted, I think I'm up to 20 or 25. I'm not sure how many plates. I have several bilateral. Libby has got even more than that. I've taken out at least half, if not most, of the plates I've put in, and I haven't had any issues. And actually, I take it out like I would any other fixed angle device. I simply remove the screws, remove the overlying bone, insert a chisel carefully between the plate and the cortex, and gentle rotation disengages the blade and you pull it out. We created this back slab hammer just in case. What if the plate broke? What if you couldn't, if you want to take out to a very small incision, you could come in, percutaneously take out the screws, unconnect the blade chisel to the plate, slip that out, and then put in the little turkey claw and backslap that out. There's all kind of different ways to do it. Have not had a problem with any removals. These are some case examples before we open up to questions. And just to show the variety, this is a failed previous DDH surgery with resubluxation revalgus. And this is a combination of a varus osteotomy with acetabular with a triple osteotomy. The next case, this is the one I showed you with the blade plate growing off the physis. This is a locking plate with a previously bone grafted cyst, re-bone grafted. And the nice thing is you can match, you put your wire up and you decide which angle you need if you weren't perfectly at 135. Once again, this knuckle is gone. The plate is now smooth because this does leave a little indenture, but that's now been rectified. This is a late congenital dislocation, again with a varus osteotomy and an acetabular osteotomy. And the case example during the technique was a PFFD valgus osteotomy. This is a young girl with a growth arrest. And this is a morsure osteotomy with both lengthening of the femoral neck, transfer of the greater troch, fixed with the valgus plate. So this little plate can do whatever you can imagine. And I'm really excited to get the adolescents with some of my young adult and adolescent deformities after SCFE and after Perthes. This is going to be a great addition to my surgical armamentarium. So that kind of wraps up the technique and the information, and we can open it up for questions.
Thank you, Dr. Steiner. That was very good.